Thank you. Thanks for coming over here and everybody who's online. I tried to make the title a little cute, from free space optics to optics in space. So we have been making optical communication components for over 20, 30 years now, and many of them are free space devices, meaning we have little piece of glass and optical materials in a little box, and ranging from interleavers to wavelength selective switches to tunable dispersion compensators. So those of you who are young enough to remember those days. But now we are essentially taking all of that and we are putting them in space in a way. So I'll start with a quick outline, a quick overview of 2.6 and our intersection in space. Then talk about what are the drivers for optical communications in space, or Spacecom in general, and then move to the emergence of the new space market. What is the new space market? It's a term that some people have started to use. What are the drivers? What are the trends? How do we segment that market? How do we size it? And then get into we are at ECOC, so get into how optical communications is enabling that part of networking. How do we take things from fiber to space? What are the challenges, and what are the opportunities? So 2.6, if those of you are not familiar with 2.6, our name comes from the periodic table of elements, groups 2 and 6. That was the history of the company. We started with materials like zinc selenide and zinc sulfide, which you can see highlighted there. These were essentially infrared materials for carbon dioxide lasers. And since then, we have come a long way. Today, we sell at all levels of the value chain, from materials to components, subsystems, and we sell into 8 different markets. And communications is our largest market segment, or almost 65%, 70% of our revenues comes from communications, and a large part of that is from optical communications. We are the world's largest manufacturer of optical communication components. But we play in multiple markets, and you see aerospace and defense, and a lot of our activity historically in the space market has been in that area. These are the markets that we service today. We are fortunate enough that all of these markets are growing very well. There are 8 large markets, and they're growing in a fantastic pace. Starting with optical communications, I mean, we are excited with the growth of optical communications. It's still on a healthy 5-year, 10% plus CAGR. But you see some markets there. Again, these are our intersection with the markets. You see automotive and energy growing at 37%, and so what's driving that? That's the electrification of the automobile, the LiDAR and ADAS and 3D sensing activities, consumer electronics. Many of us have smartphones with 3D sensing built in, so it's an exciting period for 2.6. 2.6 in space, our intersection. So we've been working on space products and solutions. We've been delivering them to that market for over 2 decades now. What are some examples of the products that we sell? High power and low power optics and subassemblies that go into various defense and commercial applications. Advanced alloys and composite materials. These are for weight reduction, for stability. You're talking about metal matrix composites, silicon carbide, structural materials. We do a lot in the area of parts for gimbal mounts and telescopes, for all the way from UV to IR. We sell specialty components that go into building telescopes for looking down, and more recently looking at each other in terms of satellite communications. And we have a pretty large area, a business area on thermal electrics and thermal management. And so there is a lot of thermal management that needs to happen in space, including generation, thermoelectric generation, or compact devices there as well. And then more recently, we are now involved in networking components and subsystems for satellite communications and Spacecom. This chart shows some of the programs that we've been associated with over the last, associated in sense delivered solutions over the last 20 plus years, and the type of products. And we sell at all levels of integration, from materials to lasers to electro-optic subsystems to complete assemblies. So that's sort of just a quick background there. So what is the driver for space communication? So why is it, why do we think it's at an inflection point? Why do we think it's at an inflection point? Well, of course, the world's hunger for data, that doesn't go away, and connectivity. But really, for the commercial market, and here I'm only going to talk about the commercial market, there are really two big drivers. One is communications. The beauty with satellite communications is that it's direct delivery to the end customer. It's the best point to multi-point solution. It gives you very wide coverage. You can go into remote areas which are impossible to connect with either radio towers or fiber. And it is a big priority for UNESCO. And these days, COVID has taught us how important communications are for just basic services and life itself, telehealth and teleeducation, et cetera. So communications is a big one. The other one is Earth observation. And this ranges from, again, strictly on the commercial side, from agriculture, forestry, when you're looking for poachers, environmental protection, traffic monitoring, disaster response. So there's a whole bunch of different areas in terms of applications that are all driving this. So what is the new space market? The new space market, the term new space refers to the commercial space market that's developing. Primarily low Earth orbit, and low Earth orbit is defined as less than 2,000 kilometers. This is a chart that shows the number of companies and what they've announced in terms of altitude. And you see only about 30 companies, but we had a filter here. We said, okay, what are to make this chart, you have to have at least 50 million in startup funding. You should have had satellites already, or you have planned launches. So it's still, the number of companies that are in this market are in the hundreds. And I'll show you another chart where you can see that. So what are the drivers? I already said the drivers are communications and Earth observation, but why now and how? And it's really the cost of the hardware has dropped significantly. Launch costs have dropped significantly, so it's easier for startup companies who have some really cool ideas of certain parts of the ecosystem to get in. And then we have the large web scalers. They're all, especially from an optical communication standpoint, we know the data centers and the web scalers and have really played a major role, not only connecting themselves, but also connecting other people. And then they went into submarine. And many of the submarine links are sponsored or run by the large web scalers. And SATCOM is sort of the next area there. Then it's right now. We already had satellites being launched into space through commercial entities, and I'm sure you're familiar with some of the larger ones. So there's sort of two economies brewing right now. There's a space for Earth economy, which has been there for a while, and we talked about, but there's also a space for space economy, essentially goods and services produced in space for use in space, asteroid mining. I mean, these sound a little far-fetched, but they're out there. The market is growing. This is the global market for space services and products, and this includes both commercial and government products applications. It's going to be $1 trillion industry in 2040. It's about 350 billion. And what is interesting is if you look at 2040, 40% of the space market, if you will, is all going to be around internet, providing internet. The chart here shows the cumulative number of satellites launched over the last 10 years and then projects out in 20 years. So you can really see on this chart, you can see the inflection happening right about now. And the prediction is about 40,000 satellites going up in the next 10 years. So it's a pretty big jump. So the way we like to, any new market, we always like to segment it. So the way we like to segment the Spacecom market, the space market overall, is first lasercom. So this is optical communications, products that we are all familiar with here at ECOT, transceiver modules, amplifiers, DWDM optics. And then the other segment would be Spacecom, where this is essentially taking the optical components, taking the RF devices, putting them in subsystems, integrating them in gimbal assemblies and telescopes, and I'll get to it in a little bit. So this essentially, in a way, you can look at Spacecom as everything that is not related to optical communications, but makes the space link happen. Then imaging, Earth observation, so this is everything to do with looking down on the Earth, looking at the mirror, looking at the moon, looking at other parts. So all the optics, silicon carbide mirrors, camera assemblies, infrared optics, and then finally the mechanical structure of the satellite itself, which we call space bus, which is the structure and the thermal performance of the satellite. And then we have a whole bunch of materials that are important in those applications. The market itself is evolving for Spacecom. There are satellite operators, there are contractors who actually make the satellites, there are people who focus on launch. I mean, there are about 100 new small rocket ventures, but 16 billion in venture capital just in rockets, rocket technology. And then, of course, we have laser-based communication systems. And the lines there are the larger satellite operators who want to make their own satellites. So the lines are moving, they're blurring, and they will be redrawn. So the advantages, I mean, this is ECOC. I don't need to explain the advantages of optical over RF for space. But for space applications, there are a couple that I want to point out. One is the spectrum is unlicensed, so which is great. So you could do whatever you want, communicate whatever you want through optical, and it's reasonably secure. It's a very confined beam, so the only way you're going to get in and tap data is come and intercept that beam, and when you do it, the signal link breaks. So there is really nothing to intercept, and optical communication components are almost by definition, they're smaller, they're reduced size and weight. I'll pick up the pace a little bit. So let's look at a typical optical communications link, a terrestrial fiber-based link, and see how it compares with what is it for a space link. So I've just drawn a very simple cartoon here, a point-to-point fiber link. We have a transceiver on one end, let's say a chain of EDFAs, not getting fancy with ROADMs, etc. And then you have a simple transceiver on the other end. And now when we look at a point-to-point laser comm, you'll find, sure, you need a transceiver on one hand, and you find a single high-power EDFA, just one EDFA. And then you have something known as a launching telescope. So this is where the beam needs to be massaged, it needs to be focused, it needs to be directed. So there is a lot of technology that goes around connecting, aligning these two telescopes. There's a receiving telescope, and around those, which we call specialty optics for space, they're gimbals, they're beacon laser. It's a laser that's typically a very high power pulse laser. It's just used to line up the two telescopes, and then focal plane detectors to again for alignment. And then we have a preamp and a transceiver. So it's got some basic components, but then it's got a lot of specialty components. That's the way we like to look at this market. Now let's look at the applications. I mean, when we make components for the submarine market, and typically you start with what you have, and then you start to adapt. I mean, we make pumps. We've been selling pumps into submarine for almost 20 years now. So we are taking the same approach when we look at these space-based applications. So what are the differences? Well, first, it needs to survive the launch. So we're talking about shock and vibe resilience that none of us have ever seen on Earth. So that comes with a whole bunch of its own requirements on stability. Then the space environment. You like to think of the space environment as very benign. When we, again, the submarine analogy, the submarine is a very, very benign environment. So typically the components that we make, it's just the reliability needs to be very long, but it's a very benign environment because water temperature doesn't change like it does here. But in space, you'd think that it's benign, but not really. There's a lot of radiation. All the electronics need to be radiation hardened. It's vacuum. The temperature range within the satellite, there are devices that give out heat, so you got to manage through all of that. And then the amplifiers, we're talking about watts, 10x times amplifiers, power level amplifiers compared to what we are typically used to in optical communications. And then finally, this is an interesting difference. These satellites that go up on space are not really meant to survive for 15 years or 25 years or 30 years that we have for fit rates and so on for optical communications products, but it's 4 to 5 years max. So that does open up some design capability for us. So these are the components. I mean, what are the components for Spacecom, for optical communication? It's the usual, whatever we have here that are for terrestrial, and we adapt them to. And I'll get into that in a little bit. And then the other part is telescopes. Telescopes are super important. This is technology that needs to be adapted for these lasers because they've been used to looking at images. Now they're now looking at signals and these high-speed detectors. These are some examples of components and modules that we have done. We have products into the Lunar Reconnaissance Orbiter. Those of you who've gone to Smithsonian in Washington, D.C., it's actually on permanent exhibit. We have 2 others that are in lunar orbit right now. And what are the materials? So here it's really we're talking about materials that are very light, that can make really good mirrors, very efficient. So here I am showing you some examples of our space telescope materials: silicon carbide housing, silicon carbide mirrors, substrate, holding mirrors. So there's just a lot of both optical as well as structural elements there. So how do we go about adapting optical components for space application? So here I'm showing a transceiver example. So what we do is basically start with what we have for terrestrial, and then we ruggedize them. This is a term that you'd often hear, COTS, or essentially means commercial off the shelf, as opposed to custom built for a defense or a government application or even a commercial application. Again, I'm showing you some examples of what what we've been doing here. So one on the top, you see just our simple 10G, 25G transceivers, fairly run-of-the-mill, but then the mechanicals are enhanced, the thermals are enhanced. We put it in special chambers for thermal vacuum. I mean, we don't do vacuum testing for any of our components, but in space you got to do that. So that is one example. And then we are adapting. I'm showing you the IC TROSA platform that won the Most Innovative Product Award yesterday. There's a lot of integration on those products. Now, when we're looking at that, say, okay, for a space application, what are again, it's really about ruggedness and radiation tolerance. There's a lot of electronics, sensitive electronics that needs to be hardened. And then there are some tweaks that we have to make. For example, if you're going to talk about 2 different wavelengths, then we need to modify the way some of these things are architected. On the EDFA side, again, those of you who don't know, we are the world's largest manufacturer of EDFAs, and we all the way from components down to subsystems. And we've been driving these things. We've been, over the last 10, 15 years, we've got EDFAs that go into transceivers, as you can see on the top, and that little tiny device. I mean, it's the size of a business card or even smaller, and our pumps are even tinier. And so we've been focusing on smaller, not for space, but for transceiver applications over the last 5, 10 years. Now we are taking all of that technology and trying to see, can we make it even smaller? Lighter is a big deal. Lighter is not such a big deal in terrestrial, but in space, weight is important and low power consumption. So we are working on but again, all these amplifiers need to be high power. So we are working on that. There are no standards for space. I mean, there are activities that are happening, but nothing like what we have in the terrestrial world. So a lot of these solutions are custom, and we really believe in the importance of vertical integration, because if they're so custom, you just have to make it yourself at the all the way down to the materials level. And I'm showing you some examples of these. Okay, so just to set us up for Q&A, if I'll just can finish this in a minute. So what are the opportunities and challenges? Surely it is a large opportunity. It's going to happen. It's going to happen like everything else. An analogy is the LiDAR market. People are talking about it happening 3 years ago. Now we know it's going to happen maybe 2 years from now. So the same thing in the Spacecom market. It is a major inflection point. It is going to be a major inflection point. There is an opportunity for the fiber optic community here to adapt the components and technologies for space. There are a lot of challenges because it needs to survive launch and it needs to survive the space environment. So that's a great opportunity and comes with the challenges. And then, so the third point is a little bit of of a unique one to Spacecom, because anything that is done in space has a military. It's applicable to military. So you got this dual use conundrum that companies need to sort out, because that translates into where the products are made, where's the supply chain, and firewalls between our military business, and all of that is what we're doing today. But that's something that the community has to consider. And then finally, the importance of vertical integration, because we believe that engineered materials underpin all of these markets, and innovations there ultimately is what's going to underpin progress in Spacecom as well. And I'd like to acknowledge Sarah, Brian, Andy, and Max. I mean, they did all of the heavy lifting, and I just came here to do the presentation.
Thank you, Sanjay. Thanks, Sanjay. So do we have any questions for Sanjay? Yeah, let me pass you the microphone.
Thank you very much for bringing us this interesting talk about the space communication market. I have 3 questions.
Sure.
The first question will be, will the space communication share the same operating wavelengths with the 5G or current communication? The second will be, what is the capacity of the optical components? And the third one, will it be the part of the Starlink project?
Sorry, I couldn't get the third one.
I know there's a plan for some company for the Starlink for launch many satellite on
Sure.
space and link together for the space communication. Will this be part of it?
Sure. Okay. I'll try to see if I can remember the first one. So the first one is the wavelengths. So as I said, this is optical communications. I mean, yes, sure, ITU is standardized a wavelength set, but it's really, you could use whatever wavelength you want. So there isn't really any, because the receiving point and the transmitting point is going to be so custom anyway. So there isn't really any standards right now. I mean, they may refer to the ITU-T, but that's just completely open. The second question was, sorry, I missed it. Sorry? The capacity. So the capacity there isn't, this is optical communications. I mean, we've got, I do have to say that the space communications market is probably 1 to 2 generations behind. So today it's mostly 10G, going to 40G. Coherent they really want to go to coherent, but it's going to take some time. So I would say 2 generations behind. And the last question about, there are multiple companies that are trying to put up their own satellites that would talk to just their satellites in their network. There's some that are coming in as a consortium. So as I said in one of my slides, the boundaries are moving. So it's something that we have to watch. I highly doubt there will be, because of the dual use, I highly doubt that there would be one uniform network for the world. I mean, I just don't see that happening.
Thank you. Is there any other questions? So I have a question.
Yeah, sure.
So with the advent of space and joyriding recently, and we can see this sort of taking off, I guess, if you've got a spare $450,000 for a ride up into space. What's the impact of that on the traditional space business per se? I mean, do you see an impact of this consumer-based activity?
Yeah, it's a good question. I mean, it's one of the things that is burgeoning or mushrooming all these companies. There are hundreds of companies that are we know the large ones, the very large ones, but all of them are focusing on various parts of it, and for sure that is a driver. I mean, if you have, I don't know what the last number was, like 15 million or something, you can go to space today. And the question is, as that increases, that's certainly another driver. But it is not space tourism itself. I wouldn't consider that to be, communications, Earth observation, and space tourism is somewhere.
Okay.
It's another driver. Let's leave it at that.
It's another driver, yeah. But it
Absolutely.
doesn't really change the way photonics is being implemented into space.
Right, exactly. I think that's really more to do with rockets. I mean, there's one slide where I showed that There are 100 startups who are focusing on small rocket technology. $16 billion of investment. So there's a lot of money poured into it, and I would think that's where a lot of the space tourism stuff would fall into.
Any other questions? All right, well, let's thank Sanjay again.
Thank you.
Thank you very much.